Okay. All right. So let's do this. Okay, so now we're going to talk about intersection of three planes. Okay, so intersection of three planes, we've got 8 different possibilities. And I know that sounds overwhelming, but it's actually really not that bad, because 4 of them gives you a solution and 4 does not. So 4 of the solutions are give you a they're consistent systems, right? Meaning that you do get an answer. And out of those 4, we can see that there is an intersection and a point. So that means that the way that the 4 planes come together, they intersect at just one point. They could intersect in a line, just like 2 distinct planes could. They could intersect in a line, but now you have 2 of the planes being coincident. So basically, this is going to be exactly like what we just did in the last lesson, because now it's as if you only have 2 planes, right? Because 2 of the planes are coincident. And then you could have all 3 planes being coincident, infinite number of solutions. Again, that's exactly the same as what we just did in the last lesson, right? Okay, so what about if it's inconsistent? Now what? Well, if you have any 2 of the planes being parallel, you know that your system's going to be inconsistent. So when you look at your 3 planes, if 2 of them have normals that are scalar multiples, automatically you know that it's part of an inconsistent system. There's no solution, right? So here we go. I've got 3 planes that are parallel, and there's no solution, right? They don't cross at all. Well, here I have 2 that cross one plane, but not in the same line, right? So again, there's no solution for the 3 planes intersecting in the same line. Here I have 2 coincident planes, and then they're parallel to the 3rd plane. So again, no solution. And then you have 3 distinct planes, but the way that these planes intersect is not in the same place. Okay, so you have 3 distinct planes and they actually form a triangular prism. Okay, so now we have to decide, how are we going to know which case it is? What do you guys think? Well, we're going to check normals, because the first thing we want to rule out is if the planes are coincident or parallel, because look how many of the situations deal with parallel or coincident planes. Okay, 2 at the top and 3 at the bottom. Okay, so that's 5 cases already that we can eliminate if we can eliminate that option. We're going to use Gauss-Jordan method to determine the identity matrix or the reduced row echelon matrix. Okay, so now depending on what happens, okay, so here's my identity matrix, 1, 0, 0 and a number, 0, 1, 0 and a number, 0, 0, 1 and a number. If we get that, then we know that we have a unique solution. That means they intersect at a point, right? I'm getting an X value, I'm getting a Y value, I'm getting a Z value. There's an intersection at a point. However, as we had seen, we could get a situation like this. So take a look at this. My last row is all zeros. So now, if I cover that row, we're dealing with the same situation that we just dealt with in the last lesson. So when you had a situation like this, where it was 1, 0, 0, 1, and then you had just your numbers, meaning Z was a parameter, what was the solution? What did this mean?
A line.
Yeah, the intersection is a line. Okay, intersection is a line because I have 1 parameter. Okay, excellent. So depending on what your matrix looks like when you solve it, that's going to help you decide whether it's a unique solution or whether it's intersection of a line. Okay, all right, so let's take a look. So here it says, determine the intersection of 3 planes. Give a geometrical interpretation. So that means, don't just tell me if there's no solution, tell me why. Are all 3 planes parallel? Are 2 parallel and 1 not? Okay, tell me exactly what's going on. So we're going to look at the normals. So when I look at the normals here, I have 3, 1, 2, 0, 3, negative 2, 2, 1, 1. What do you guys think? Are they parallel? Are any of these planes parallel?
No.
No. Okay, so now we know we have three distinct planes. So we have to put them into an elementary row, into the matrix, and start using our solving techniques to reduce it, okay? So here I have 3, 1, 2, -7, 0, 3, -2, 2, 2, 1, 1, -4. As I'm showing on the side, we want to get this into 1, 0, 0, 0, 1, 0, 0, 0, 1. If I succeed in doing that, it means there is a point of intersection. Okay, so here, guys, all we're going to do is reduce I'm not too concerned about the actual strategy of reducing this. We talked about that in yesterday's lesson. What I want to talk to it about is the result. So there's a series of steps. We always do it the same way. Get your 1 first, then the zeros in the column. Go to the next column, get your 1, then get your zeros. You can do 2 steps at once, okay? Until you get that 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, and so far it's looking good here. I've got my 1, 0, 0, 1. It's going to depend now on that last row. And here I've got my 0, 0, 1. It's looking pretty good. I've got 1, 0 there. I've got 0, 1, 0, 0, 1. Looks good. So now when I keep solving, I succeeded. 1, 0, 0, 0, 1, 0, 0, 0, 1. That means the 3 planes intersect at a point. What is that point? 1, -2, -4. Okay? Intersect at a point. Are there any questions? Okay. Determine the intersection of 3 planes. Again, give a geometrical interpretation. Here are my planes. And I noticed that I have normals 1, -2, 3, 1, 1, -1, 2, -4, 6, which can be reduced. And when I reduce it, I notice that it is 2 times the first normal. So what does that mean? Well, it means that my first and my third plane are either parallel or coincident. So I'm not sure which one. So how do I figure out if they're parallel or coincident?
D value.
Yes, you check the D value. So I check my D value. So just by looking at it, I've got 9 and then I've got 5. They're not coincident, right? 5 is not 2 times 9. And so therefore we see that there is no solution. So for the geometrical interpretation, what do you have here? You have 2 parallel planes and the other plane goes through them. Okay? And there's no solution. 2 parallel planes and 1 distinct plane. Okay, so the 1 distinct plane is going through the 2 parallel planes. And so you have no solution. All right. Determine the intersection of 3 planes. Give a geometrical interpretation. So I've got my 3 planes and I take a look at the normals. 1, 1, 2, 3, -1, 14, 1, 2, 0. None of these can be reduced. None of these are scalar multiples. So therefore I take a look, or none of these are the same, I should say, once they're reduced. And so therefore we know that it's 3 distinct planes. Let's see if there is a solution at a point, solution at a line, or no solution, because it could form a triangular prism, right? So let's see what happens. Those are my 3 options now. Now that I know that I have a distinct plane, they can intersect at a point, they can intersect in a line, or they can form a triangular prism. So now I've broken it down to 3, right? Or I've narrowed it down to 3, I should say. All right, so here we go. 1, 1, 2, -2, 3, -1, 14, 6, 1, 2, 0, -5. So I want to start by making that first row, first column 1. Well, it's already 1, so I'm good. So now I need a 0 below it. So I'm going to I need 3, take away 3. So I'm going to multiply that first row by 3 and I'm going to subtract, right? And there I get my 0. And I want to get the other 0. So I'm going to take the third row and I'm going to subtract the first row. And it gives me this. So there you go, 1, 0, 0. So far, success, I'm doing well. I go to the next column. I want to make that -4 a 1, okay? So I'll go ahead and I do that. And now we're going to try to get zeros in that column. Well, when I do that, look what happens. I ended up with one whole row being 0, 0, 0, 0, 0. Well, 0z equals 0 is a true statement, right? No matter what I sub in there for x, y, z, I'm always going to get 0. So it's a true statement. Because it's a true statement, that means that the intersection must be a line. There is a solution, right? And so now, from here, just this now, when you look at this problem, this becomes the exact same as we just did. We're going to let our parameter z, or z be our parameter t, so let z equal t, and we're going to get our solution that way. So you're going to have x plus 4 equals 1. We're going to rearrange it to get x equals 1 minus 4t. Do you guys see that? From here, I have y equals, and it would be 2z minus 3, and z is equal to t. Okay, so there you have it. 1 minus 4t, y equals negative 3 plus 2t, and z equals t. Are there any questions? So this case right here, the intersection of a line, we've already looked at. So it's the exact same solution as we just saw in that 9.3 lesson. Okay, so what's the geometrical interpretation? Well, we've got three distinct planes that intersect in a line. So going back, three distinct planes that intersect in a line. We've got this case. All right, example 4. So same question, here are my planes. So I look at the planes and I notice that they're distinct. So if they're distinct, right away I'm just going to go to my matrix, sub it all in. Again, the strategy is the same. Start with that 1 in the left, which is already there, then get the zeros below it, and then go to your second column, second row, make that 4 a 1, and the other 2 zeros, and you keep going. So as you're working, you notice that you get 0, 0, 0, and a negative 7. Well, 0 does not equal negative 7, and 0 can never equal negative 7. So in this case, we notice that we have a false statement. Well, if there's a false statement, that means there's no solution. But I have three distinct planes. So if I have three distinct planes and I have no solution, I must be this case. Three distinct planes, but it's inconsistent. Oopsies. Oopsies. What happened? It moved. There we go. So three distinct planes, but it's inconsistent. Well, that's this guy. So it forms a triangular, the three planes form a triangular prism. Okay?
Miss,
Yeah.
could we already have seen that from the second matrix, since 4x minus 11z equals two different numbers?
Yep. You can, but you have to get it down to the last step. You got to finish. You can't stop.
Okay.
Yeah, you have to finish it, right? You're right. Just like you would see it here too. Like, look, at one point you're gonna get a whole. Hold on a second. Let me see where it is. Where is it? Where is it? Right here. Like, look here. Look at this step. You see that? You see that you have two lines that are exactly the same. But you're not gonna stop there. You're gonna bring it to the last step.
Okay. Thank you, Miss.
Okay. Yeah, no problem. But yes, and this happens pretty quickly, to be honest, when there is no solution like this, or if there is an intersection in a line, it usually happens within 3-4 steps. It's not like 15 steps and then you figure it out. Sorry, guys, just give me 1 sec. 1 sec. Sorry, guys. Okay, let's go back. All right, I think we had, is that it? We didn't have one more example? Nope, that was it. Okay, so you have three distinct planes that form a triangular prism. All right, guys, so this is the homework for this section. Page 530, numbers 4, 5B, 6, 8 to 10, and 12. Okay, so let's talk about